parse here. I guess serial communications didn't appeal to a lot of folks today. But it's actually quite cool in a geeky sort of way. So we'll start off with the usual public service announcement. Remember that if you're going to do a rewrite on your lab reports, they are due tomorrow. If you have any questions, feel free to stop by Crosby at any point today. I'm going to be hanging out and grading and just doing stuff. So if you need help, by all means, come see me. Okay, serial communications. This is hugely important in real machine design, folks. We need to have our machines either talk to other parts of itself, or maybe go out and talk to the real world. In order to do that, you gotta have standards. So first off, what is serial communications? It's just a bunch of ones and zeros. And it can be either 0 volts or 5 volts, 0 volts, 3.3 volts, or if you get into some of the actual RS-232 serial, you can go plus or minus between -5 and 25 volts to be something like that. So let's say we want to transmit the word hi, okay, between two serially connected devices. Okay, we're going to use the standard called ASCII, which is the American Standard Code for Information Interchange Character Table. You will never remember that again. I don't remember that. It's just ASCII. And it looks like this. So every character has a unique number that corresponds to it. So for example, H corresponds to the ASCII value 72. And I, lowercase I, is 105. So we need to send the numbers 72 and 105 on the data lines to say hi. So we're going to convert that to 8-bit binary. Here's the process. So if I want to convert 72 to binary, the process I always use is I say, okay, can I subtract 128 from 72? No, because that would result in a negative number. Can I subtract 64 from 72? Yep, sure can. So I put a 1 in there. And then the remaining 8, I say, okay, can I subtract 72 from the 8 without going negative? No. Can I subtract 16? No. Can I subtract 8 from the remaining 8? Yep, sure can. So I put a 1 in there, and then I have nothing left, so it's all zeros. So if I want to express 72 in binary, it's 0, 1, 0, 0, 1, 0, 0, 0. Cool? Let's do the same thing for I. So 105. Can I subtract 128 without going negative? No. Can I subtract 64? Absolutely. So that's going to leave me with 41. Can I subtract 32 from 41 without going negative? Yep, sure can. And that's going to leave me with 9. Can I subtract 16 without going negative? No, 0. Can I subtract 8? Absolutely. That leaves me with 1. Can I subtract 4 from 1 without going negative? No. 2? No. And I can subtract 1 from 1 without going negative. So 105 in binary is that set of digits. Okay, cool. So now I got my 1s and 0s. But now we have to properly format it so we can actually transmit it. And we're going to do this by adding a start and stop bit. So your start bit is going to be a 0, and your stop bit is going to be a 1. When you're transmitting just plain Jane serial data, folks, you always leave the data line high, 5 volts. And basically what that's telling the computer is, hey, something's connected. If it was 0, you wouldn't know if there was anybody to talk to. Okay? And then when you want to start your transmission, you pull the data line low. And that's that start bit. That's why it's 0. You pull the data line low, and the controller says, oh, okay, I got an incoming message. So it's got 1 bit worth of get ready time. And then it times it, and you're going to send bit 0 first. So you send bit 0, bit 1, bit 2, bit 3. It's kind of backward of the way I think of it, but okay, as long as you do it right. So you send 0 through 7, then you have a stop bit. So you let the line go low to say end of transmission. And then you're going to have another start bit. Well, you send it low, then you stop for a little bit, put it back up at 5. Okay, you always start with your transmission at 5 volts. You got another start bit, you pull the line low. Okay, I've got 1 bit worth of starting message. I send my message again. I do a stop bit, I send it 1, and then I let it go back up to 5. What that does is by having a start and stop bit is you can actually look and see if you have a correct message. If you don't get the correct start and stop conditions, you can reject that byte of data and say invalid. And by doing that, what actually happens is your transmission becomes self-correcting. So you might get a bunch of gobbledygook characters, but eventually what will happen is it will start settling on the start bit, and you will get correct characters. I probably should have demonstrated that. It's kind of neat when you see it. Okay, and here's what it looks like. So I actually did program the Arduino to set high on the serial line. And here's that, so I triggered a pulse right here just to say, here's the start of my transmission right on this line. And that's right here. So you see the 5-volt line goes low for 1 bit. And then my transmission starts. And then we come back up to high. And if you break that down, it actually looks like this. So here's my start bit. So let's see, that's 1, 2, 3, 4, 5, 6, 7, 8. Low, we go back high. So this is like the resting position between characters. And then we pull it low for another 0 start bit. We send the high, stop bit, and it goes back to high. Okay, and that's probably the simplest standard communication protocol out there. It's generally called TTL, transistor to transistor logic. The key to making this work, however, is you got to very precisely time the whole thing. And that's where you get into talking rings, or baud, which is bits per second. And the common ones are 9600. 9600 actually came from the old fax machines. That's as fast as they can talk over a telephone line. Then we went up to 14.4 when we got really hot in the 80s. 57.6, and a lot of times now, for the stuff I do here, I use 150 and 200. So you will see the term parity used. Okay, that's just an error checking algorithm that's commonly used. So we use it for detecting errors. When parity is used in the serial port, we add an extra data bit so that the number of 1 bits in each character, including parity, is always even or odd. Just another way of checking on top of the start and stop bit conditions. Okay, so that's TTL transmission. That's what you see if I just tell the Arduino to say hi. If I wanted to say hi between two computers through the serial port, I mean, you guys don't see old school serial ports anymore. But back when we had those, they would have a bipolar signal. So you would either see a portion that's +5 to 25 or -5 to -25. And that was called RS-232. RS-232 did have flow control through something called handshaking. So if you look at an old school serial port, it looked kind of like this. So you actually had a bunch of data pins in there on the back of the computer where you could say, request to send. Hey, I'm ready to talk. Or you could say things like, the terminal's ready. A lot of these have gone by the way of the dinosaur folks. They're not out there anymore. But they were a thing back in the day. So like if the clear to send was not high, the other computer would stop talking and let it catch up. Maybe the data had to be buffered so it could be written to an old slow hard drive, something like that. That's where you really needed flow control. Today everything is so fast, it's kind of not an issue. Let's see. Stepping it up a little bit, the next fancy thing is I2C. I2C is a little bit different. Okay, with I2C, rather than just timing the pulses, what you're going to do is you're going to have a strobe line. So you're going to see a dedicated conductor that says, okay, I'm going to go +5 volts, 0, +5 volts, 0. And every time it goes high, you look at a separate data line and you say, what's the condition? And that's my data bit. So now I can talk a whole lot faster and more reliably. Problem with I2C, however, in my opinion, is in the messaging, you have to include a device address. The nice thing about I2C is I can connect a whole bunch of sensors and stuff to a data line, to a data bus. And each of those nodes on the data bus is going to have a different address. And that's how I control who I'm talking to on the data bus. They're a little annoying because they're all hardware set. So if you have something like our little demonstration for today, you might have, I don't know, like on this little breakout board right here, you might have a bunch of dip switches that you would set, and that would set the address. And then you'd have to go into your master controller and say, okay, when you're talking to location 64, that's this particular board. Okay, so you'll see I2C out there. It's used a fair amount. If you want to get even snazzier than that, however, you can do SPI, Serial Peripheral Interface. Almost exactly the same thing. The big difference between I2C and SPI, however, is with SPI, you have a talking line and a listening line. So you still got the same strobe, you still got the same addressing issue. It's just you're not putting everything on one data order. So you got to send and receive one. Great. Who cares? Why do I need to know this? Okay, that's what I always said when I was in the air chairs. Okay. The important thing about this is that you know it exists. It's like a lot of stuff in engineering. So when you go and design some product for Boeing or something like that, you got to remember to make room for all of this stuff in your designs. Do not try and scab it on afterward. It gets really, really ugly. And it's very, very common. Okay, we're going to do one last protocol, which is CAN, Controller Area Network. This one, in my opinion, is the absolute stuff because it is the central nervous system of every car on the road today. And the nice thing about CAN, there's no addressing. You can do it all in software. And that is what this little doohickey on my daily demonstration is. This is actually the central nervous system of a car. This module right here, that thing could be your engine control module. This could be your climate control module. This could be your headlight control module. And the only connection they have is these green and black wires. Your data high and data low. That's it. But these things can talk bidirectionally. They can talk asynchronously. The nice thing about it is the CAN protocols, by nature, control collisions. So when you send an ID for your message, that contains who gets priority to talk. So for example, let's say that I'm driving along and I fall asleep and I hit a tree. Now all of a sudden there's an oak tree coming up my hood at 60 miles an hour. I probably want those airbags to go off. I don't really care if the data transmission for my seat position sensor finishes talking. I want that damn airbag to go off. Okay, that's what CAN does. So the lower the CAN ID, the more priority the message has. So if I have the CAN ID of like 0001, and that message is going to have priority. That's going to be like my airbag deploy message. You can have CAN IDs up to 2048 different messages. And anybody, any of these modules can send any CAN ID they want. So if for some reason your power seat module over here decided to send an airbag deploy message, it could do it. It could absolutely do it. Never does, but it could. And here is what a CAN bus network actually looks like, folks. This is what's on the table right there. So you got a high data line or an H data line. You got a low data line. You terminate both ends with 120 ohm resistors. And then you have two lines that come into your CAN controller. And that's it. That's all there is. Which is absolutely beautiful. Okay, so everybody, the ride height control can talk to the climate control, can talk to the wipers, can talk to the lighting, can talk to the main CPU. So literally, I can take this thing that's on the table, I can plug this in under the steering wheel of your car, and I could unlock your car if I knew the proper CAN codes to send. Or I could sit there and make the tachometer go back and forth with the engine off. So, yes, you can cause all kinds of fun games with this. Hopefully the Formula SAE guys will take this class at some point. And the reason they went to this, folks, is simply because cars got complicated. And you don't want to have this really bulky wiring harness where you're going to take, say, your ride height module, bring that all the way back to the main computer. You don't want to have your tachometer stuff all coming back to the main CPU. You want to have distributed processing. And in a typical car today, you're going to have like 70 microprocessors controlling each of these individual modules, and then you just send the two wires back so they can all talk to each other. So really, really streamlined. Okay, and this CAN stuff is not just used in cars. It's used in medical instruments, it's used in HVAC, it's all over the place. Let's see. I already told you about everything on that slide. So, limitations. CAN accommodates 2,048 different report styles, which I just told you about. It's got a top speed of 1 million bits per second. Holy smokes, that's fast. At least today. Might be slow next week. But today it's fast. CAN bus is dependent upon the length of your network, which, it's not hard to imagine. The longer these wires become, the more inductance they have. The harder it is to just plain charge the wire, put a magnetic field around it. So if you're under 40 meters in length, you can go up to 1 million bits per second. You can go out to 1 kilometer if you derate it down to 50,000 bits per second. Is that important? I don't know. Depends on your application. If I'm pumping oil in an oil field, maybe 50,000 bits per second is not that big a deal. If I'm just gathering data. So as always, we have a demonstration. And this is probably the most overkill system for moving a toy airplane servo ever created. So I've got 3 Arduinos, all separately powered. I don't even have their grounds connected, so they can't even talk to each other, except through the CAN interface modules, which are these little boards right here. So a serial communication comes across, comes into the CAN controllers, and the CAN controller just sits there and it waits for a transmission to come on the data lines. If a valid transmission comes along, these little boards put up a high bit line, which the Arduino interprets as an interrupt. And the interrupt says, okay, a message came in, you need to go look at it. So let's fire this thing up. I found it's really touchy about battery voltage. So hopefully I don't have any issues. Yep, I get it. Let's try that. Aha. Okay, so I've got you loser. All right, I will just tell you, I've got blinking light And I got blinky lights going on. So I am talking over my high and low data lines on the CAN bus. Why is this thing cutting out on me? Okay, so I'm moving the pot, and what it's doing, let's actually check the data coming in. Hopefully this doesn't kill everything. Okay, and here's the data coming in. So with CAN, here's my ID. That's establishing the priority of the message. And then you can have 8 data bytes following the CAN ID. And for transmission, I set them up here. They can be any 8-bit number, so it can be 0 to 255. Those are like straight charge makes this thing nuts. Okay, so what's the last entry? You can see that last data bit is changing. And I'm transmitting that data right here. So I read the analog A0 port, divide by 4, so I'm within range. I have to send it as character data. And the data shows up over here. So CAN is not real hard to use, folks. It's a pretty easy protocol. And you'll find that a lot of the new breed of microcontrollers that are out there, they actually have CAN right on board. So the new Arduino R4 Minimas, they even have CAN built in. So all I got to do is run the high and low lines, and I can stack a whole string of Arduinos together and talk with high-speed CAN. Really, really nice protocol. So just know it's out there and it's a tool you can use. Now I'll leave you on this note. Where's my sound? When I saw this, I thought it's going to be absolutely great for class someday. But of course it will not play.
You have to select the audio output for the speakers and the options.
Say again?
For your audio output, is it saying that it's your computer's output, or is it for these speakers that might be an option in the drop down menu?
It usually goes through the whole AV system in the room. That's what it's done every other time I've tried to do this. All right, I got my speakers, but not. Now, why is this not just absolutely blasting right now? All right, anyway, I was going to leave you on that note. But in the movie The Martian, we got our poor astronaut who's trapped on Mars. And he's trying to figure out how to talk to mission control back on Earth. And he realizes he's got a very limited ability to communicate. All he can do is turn the camera. So what he does is he sends the message in hexadecimal, which is the base 16 counting message or method. I'm just waiting for this to blast. All right, anyway, you can watch it in class notes. It's a really good scene. And that thing he's looking at, that is the ASCII chart that I just showed you. The difference between that chart and one I showed you is he's got it in base 16 so that he can have a smaller number of characters. Watching it in notes, it's pretty, in the class notes, it's pretty good. All right, that's all I got for you guys. So.